Morning, guys. Today we're going to go over water supplies. This is an extremely different slide to go through under normal conditions in a classroom. So I'm going to go through this at a little slower rate and hopefully get it so that well enough explained so that you can go through the calculations for this. The things we're going to go over: why treat water, the uses of water, water supply systems, sources of water, water treatment, water storage, distribution systems, definitions, and calculating water supply pressure, which is to make sure that you have enough water at the tap or at the shower head in your house to effectively run whatever utility it is you're using. And we will get into the difference between volume and pressure here. Some of you people may have been in the shower at one time or another in your house or in some other place where someone flushed the toilet or ran the water, and then you had a huge drop in pressure. Your shower didn't want to come out. That is from volume, the amount of water, not so much the water pressure. And that can be caused by a lot of variables in a system inside of the house, depending upon how it was plumbed. Okay, why do we treat water? Society realized long ago that human health and the welfare of the general population are improved greatly if public water supplies are treated prior to use. Nearly all structures require a water supply. Appropriate flow rates, pressure, and water quality are necessary for effective use. The uses of the water: what's it used for? Okay, bathing, toilets, cleaning, food preparation, cooling, fire protection, industrial purposes, and drinking water, or what is referred to as potable water. Today, almost all commercial, industrial, or residential structures must have a water supply. Water is also used for such things as bathing, toilets, cleaning, and so forth. So a water supply system. Civil engineers are responsible for designing these systems that provide a reliable and clean water supply. A water supply system begins at a water source, and water is transported to a treatment facility where the water is treated to ensure the supply is safe. And then once it's treated, the water is transported to a storage facility, for example, a water tower, where it is stored for future demand. When a water faucet is opened or a fire sprinkler is activated, water is transported through the distribution system to the consumer. Different sources of water: aquifers or groundwater, which is the water table. Here they're showing this, a saturated zone of groundwater. Without this, a well pump will not work. It has to be reached down to the saturated zone. Aquifers, primary source of drinking water, porous consolidated rock or unconsolidated soil. Groundwater fills the spaces that are in between of that. Surface waters: lakes, reservoirs, rivers that are dammed to create reservoirs. Reservoirs store water during heavy rain and snowfall. Water treatment: that's the amount of treatment depends on the quality of the source. Groundwater requires less treatment than surface water. The method of the water treatment and the size of the plant are dependent on the quality of the water supply being fed to them and the water demand. In general, groundwater requires less treatment than surface water because surface water is exposed to more contaminants, pollution, and so forth, where water from some private well sources may require no treatment, because it's using ground and sediment to filter that water. The City of Winston-Salem Water Treatment Facility withdraws water from the North Santiam River. And normally, I would have a gentleman come in from the City of Winston-Salem to come in and go through our city's very rich water supply system, because it's one of the oldest designed water systems in the United States. Guy usually gives a great presentation too. This is just one more thing that I'm really, really sorry that you guys are missing out on. Then the water is pumped to a storage, tank where water pressure and treated water is pumped to store the water there. Tanks are often elevated to provide pressure. A storage tank serves two purposes. It stores the water until it's needed, which reduces the peak demand on the treatment facility, and the elevated water tank creates pressure in the entire water distribution system. For every 1 psi is equal to 2.31 of feet of water. The water distribution system includes all of the water lines, the components, everything that is attached to the water lines. There are basically two different types of distribution systems and configurations: a loop system and a branch system. Okay, a loop system is more desirable than a branch system because it has isolation valves, so water flows in more than one direction. The drawing on the left, you can see two arrows coming straight in towards the center, one from the top, one from the bottom. Okay, with a loop system, if there's a break anywhere in that system, people within that block and that served area continue to have service. Whereas the branch service that is has one inlet, only one inlet, one outlet. If there's a break anywhere in there, you have to shut off the water to everybody's houses to fix it. Loop systems are more desirable because they provide redundancy. If a leak occurs, it's easily isolated and can be shut off and then repaired. Also, the loop system allows water to flow from more than one direction, which can reduce the negative effect felt in a branch system when the houses closer to the input start using water. The houses farthest away from the input have lower pressure, which is really negatively impacts those houses. You see that a lot out in rural systems, not so much in city development. New systems are often constructed with thermoplastic or ductile iron piping because the efficiency of the system depends on a smooth interior pipe surface. Cement linings or coatings are sometimes used to reduce pitting and corrosion associated with iron pipes. For larger diameter water mains, reinforced concrete pipe is often used. Cast iron pipes and asbestos cement pipes have been a popular choice for water distribution systems in the past. So you may encounter these materials when tying into older existing systems. A distribution system pressure of 65 to 75 psi is often recommended. Pressures over 150 psi though can cause leaks and damage to the system, so they are pre-regulated before a system to bring it down, if that's the case from booster pumps or high volume pressure systems. Consumers. Who are the consumers? Residential, commercial, industrial facilities. For residential purposes, minimum distribution pressure is 40. If it's less than that, it needs a backup pump. Maximum 80. If it's more than 80 psi, you've got to install pressure reducing valves or adjustable valves. Commercial or industrial facilities, though, may require higher pressure, and usually they use very, very, very large pumps to increase the pressure for that. Most water system supplies can adequately serve all customers, including residential, commercial, and industrial facilities. For residential consumers, like I said, 40 psi is a minimum, and a pressure over 60 is considered high. Because it increases the flow rate, high water pressure can lead to increased water use or waste and increased energy use due to the heating the excess water. In addition, high water pressure can damage appliances too. If you've ever turned the water on and shut it off and you hear a big whack, that's the water pressure coming to a stop in the pipes. And building codes often require pressure reducing valves at the service meter when the distribution pressure exceeds 80 psi, like I said. Getting into some definitions. In fluid dynamics, head can be measured by the height of which water rises in a column when directly open to the water. Static head is potential energy of the water at rest measured in feet of water, and this changes in elevation between source and discharge. So you have the initial height of the water tower and then the ending height at the faucet or the house. What is a static head at a residential supply line? If the water level in the elevated tank is 943 feet and the elevation at the supply line is 890 feet, you would subtract the two. 890 from 943 feet equals 53 feet of water. Static pressure. That's the pressure of water at rest. So when your valve or your sink is turned off, it's the amount of pressure in the pipe. It's measured in pounds per square inch, and 2.3 feet of water height for a tank equals 1 psi. So what is the static pressure at distribution? If the static head is 53 feet of water, this would be the formula here. We work 53 feet times 1 feet over 2.31 feet, which would give you 22.9 pounds per square inch. Is this the pressure at which water would exit a faucet on a house? How far above the supply line must the water level in a water tower be in order to provide 40 psi? That would be 93 or 92.3 feet. Except water loses pressure as it travels through pipe. Water loses pressure as it goes through every time there is a left turn, a right turn, a T-valve, a reduction in the pipe size. Head loss is considered the energy loss due to friction as water moves through the distribution system. Pipes, fittings, elbows, T's, reducers, all of these things are head loss. Major losses equal the head loss associated with friction per length of pipe. And to figure these, minor losses is head loss associated with bends and fittings and valves. Normally we would go through the Hayes and Williams formula. There's several methods that can be used to estimate head loss in a system. We would use the Hayes and Williams method and equivalent length approach, which to calculate the head loss in straight pipe, use the Hayes and Williams formula, and to be careful to use the correct units when substituting values for the variables. The value of the Hayes and Williams constant depends on the type of size of pipe, and it's taken from a chart of accepted values which you don't have. And I'm going to quickly go through this because in order to have you actually work with this, I need to provide you with a pamphlet of paper about 10 pages thick so that we can do the exercises that are calculated along with this PowerPoint. It's very difficult for you to do just watching me present this. As a matter of fact, it's absolutely impossible for you to do unless I deliver these papers to you and then or have you print them all out so you have them in front of you, which is a little bit extreme to ask your parents to do for one PowerPoint presentation. So I'm going to go through this a little quick. The Hazen formula equals head loss due to friction in feet. L equals the length of pipe in feet. Q equals the flow rate of water in gallons per minute. C equals the Hazen-Williams constant. The Hazen-Williams constant depends on the type of size of pipe and is taken from a chart that would have come with the handout that goes with this. And this would actually be a 2 to 3 day activity that we would do in school. This is the Hazen-Williams constant C chart. These are the values that would be associated with this. The constant depends on the type of the pipe and also the condition, because cast iron pipe gets pitted and increases the friction. Most pipe will experience pitting and corrosion over time, so as the pipe ages, the friction of the water against the interior surface of the pipe increases. Because the Hazen-Williams constant is in the denominator of the formula, a decrease in the constant will result in an increase in the frictional head loss. You'd be able to see in the table the constant used for design is less than the clean new pipe constant. So the design values assumes the pipe has been in service for a number of years, and that's the way you would design it too. You can probably guess that steel and iron will deteriorate over time much more drastically than copper or plastic. This is indicated in the table by the difference between the clean and design constant values. The difference is much greater for steel and iron than for copper and plastic, and you can note that the lining steel or iron pipes with cement will significantly reduce the increase in head loss over time. Minor head losses. When considering these, I'm sure you can imagine looking at this picture, you got two sharp edges. Think of it like a car. You're not going to be going along at 100 miles an hour, hit that right-hand turn, and then another left-hand turn, and still be doing that same speed, all right? When water has got to make a turn or squeeze through a valve, it's going to lose its energy and its volume. The Hazen-Williams formula does not directly account for the minor losses due to fittings. So in order to use the Williams formula to approximate head loss in a system, you convert each fitting into an equivalent straight length of pipe. In other words, we need to know the length of pipe that produces the same head loss that results when water flows through a fitting. For instance, a 90-degree elbow might produce a head loss that's equivalent to the same head loss when water flows through 14 feet of straight pipe. Therefore, the equivalent length of the 90-degree elbow would be 14 feet. So you just add 14 feet to the equation by adding the equivalent length of each fitting to the actual length of the straight pipe, and it's easier to figure that way. So we obtain a frictionless or a fictitious total equivalent length that should yield the same head loss that results in the system. And there's a huge tablet of equivalent lengths, but this one here just gives you an idea. For elbows, right-hand turns, a regular 90 degree, you can see that as the size gets larger, the length increases and adjusts according. Long radius 90 degrees, those are more of a sweeping curve, not a real sharp turn. Regular 45 degrees equal a different length. Same thing with T's, return bends, and valves as well. For example, a 10-inch flanged cast iron water supply line provides service to a home. The pipe between the water tower and the meter includes 7 regular 90-degree elbows, 3 line flow T's, 11 branch flow T's, and 6 gate valves between the water tower and a service connection to a residence. We would now figure out what is the equivalent length of the fixed fittings in the valves. I would have you guys get into groups of 3 and do this. We would look at the chart here, come up with the total. The pipe length equals to 3.2 miles, or 5,280 feet in a mile. So we come up with 16,896 feet, which is the total equivalent pipe length for the pipe and the fittings. So we add that all together, and it equals 17,358.8 feet. We plug this into the Hazen-Williams formula, and what we would come up with is 2.94 feet. When we talk about dynamic head, that's the head of a moving fluid. That's measured in feet of water. So dynamic head equals static head minus head loss. The terms dynamic pressure and actual pressure are used interchangeably and can be calculated by converting dynamic head into feet of water to pounds per square foot, and then to pounds per square inch. Water pressure calculations. The water level in the water tower supplying the home in the previous example was 1,487 feet. The elevation of the supply line at the residence is 1,246 feet. We would find the static head, static pressure, and dynamic head, the actual pressure of the water as it enters the residence. This would be figured out like this. The static head is different than the elevation between the water head and the tank, the supply line level. You guys would then calculate this. We would go through this, and we would come up with a dynamic pressure, working pressure of 103.1 psi. And for our residents, this would have to be reduced. Okay? So, again, I apologize for this long presentation, and I hope you got a better understanding out of the use of the terms and the formula that we use to calculate this. And when the pressure's not high enough, a civil engineer comes in and designs a lift pump station to accommodate a specific area. And the one presentation that I have for you guys, the guy from the Winston-Salem City Water Department comes in and does a great layout for you for that, and I wish I could somehow get him on, but right now they are understaffed. I did contact him about trying to do a remote presentation, but that was not possible due to the corona things here. So that's all I've got for you today. Please read the haiku page and follow up with the Quizlet Unit 5 activities, and then please get caught up with any missing activities that you may have. And I'll see you guys tomorrow. Thanks again.